Okay, perfect. So yes, Christian Offen will present his work on symmetry and numerical analysis aware learning of dynamical systems from data. So thank you.
Thank you, David. So I would like to show you how you can improve learning of dynamical systems by using tools from differential geometry and from numerical analysis to regularize the learning procedure. Okay, so which kind of problems are we looking at? So we are trying to learn a dynamical system from data, and the data that we have are discrete observations of motions. So these can be trajectories, these can also be solutions of PDEs on a mesh. And why would you like to do this? Well, you would like to interpolate, you would like to extrapolate, or maybe you want to learn a dynamical system to understand its properties better. So for instance, you want to learn a dynamical system to find very symmetric solutions of the dynamical systems, like traveling waves in a PDE. Okay, and a good idea is to use prior knowledge when you're learning a dynamical systems, and a lot of people are working on this, and they incorporate lots of different geometric knowledge. For instance, we've seen incorporation of symmetries, incorporation of Hamiltonian variational structure, or just the mere fact that you know that although you've got discrete observations, that the underlying system is continuous. Okay, and what I would like to show you, so I will concentrate on Hamiltonian and variational structure today. And when you learn these systems with especially variational structure, you would like to find a good representation that helps you later on in your numerical simulations. And for this, we will develop regularizers that are numerical analysis informed. So this makes the system take a representation that is very good for numerical aspects. And we do more regularization by developing regularizers that pushes the model of the dynamical system into a symmetric representation. Okay, so a repetition, what is variational structure? So a system, a dynamical system with variational structure means that the solutions are governed by a variational principle. So solutions are stationary points of some action functional, which is equivalent to saying that the motions solve this second-order differential equation, the Euler-Lagrange equation, and a popular way of learning these systems are to learn the Lagrangian L. And there are extensions of this where you include external forcing terms and so on and so forth. You can do this on a PDE level as well. So there you learn the Lagrangian density functions. So here solutions of the field equations are stationary points of this action functional, which is equivalent to being stationary points of this PDE. And you could think of learning the discrete Lagrangian, the Lagrangian density from data. But one thing that is a little bit more clever than this is, rather than trying to learn the continuous Lagrangian density when you are actually observing your solutions on a mesh, is to discretize everything. So to repeat all of this in a discrete setting, so you use discrete mechanics and try to learn the discrete Lagrangian density, because that's a very clever thing, because once you've done this, you already have the discretization that you need later on in your computations. So that's a clever thing, and if you repeat all this derivation here, then you get discrete Euler-Lagrange equations, and you get discrete Euler-Lagrange equations in the PDE case as well that you can use for computations later on. So you don't need to discretize later on, and you also don't need to approximate velocities or acceleration data. Okay, so let's learn the discrete Lagrangian density. But there's a very, very big problem when you do this without assuming more prior knowledge, is that this is not at all well defined. So motions can be, so there can be many discrete Lagrangians that govern the same motions. So let me demonstrate this. So say you're observing linear motions, And there are now many, many discrete Lagrangians that govern linear motions. So take any g defined on Rd, scalar valued, and then you can build this discrete Lagrangian here. And the discrete Euler-Lagrange equations, they look like this, and the solutions are linear motions. And, well, this is great, but this also means that the discrete Lagrangian is not at all determined by the motions. But if we now just parameterize the discrete Lagrangian by a neural network and then try to make it fit, then it really depends which one we pick, whether the discrete Euler-Lagrange equations are easy to solve or not. So in the worst case, you just learn a constant Lagrangian, which is compatible with any dynamical system, but of course this doesn't give you any idea about, then you can't solve the discrete Euler-Lagrange equations. So we would like to learn a good discrete Lagrangian. And what is a good discrete Lagrangian? A good discrete Lagrangian gives me discrete Euler-Lagrange equations that are easy to solve and extrapolate well. And one idea to extrapolate well is that LD is as symmetric as possible, because also symmetric dynamics can be governed by non-symmetric discrete Lagrangians. You don't want that. You would like to learn a symmetric representation. So we will focus on these two regularization strategies today. Okay, let's start with the symmetric part. So the idea is not just to learn the discrete Lagrangian, but at the same time you try to learn the symmetry of the system. So here we assume we don't know the symmetry a priori. We just want to push the discrete Lagrangian into a symmetric representation. And the idea here is to make an ansatz of a symmetry group, a very big symmetry group. For instance, affine linear transformations. And then you try to learn, at the same time as learning the discrete Lagrangian, you are trying to learn a subgroup of that symmetry group that acts by symmetries. So let's take the affine linear group. Okay, so then you pass to the Lie algebra. So the Lie algebra in this case can be understood as matrices and vectors, and each of the elements in the Lie algebra corresponds to an infinitesimal symmetry. So for instance, any skew-symmetric matrix here corresponds to a rotational vector field, and then you can check whether your Lagrangian is invariant under infinitesimally invariant under rotations by just computing the directional derivatives into the directions defined by this vector field. So the idea now is not just to learn the discrete Lagrangian, but at the same time to learn a linear subspace in the Lie algebra, such that every element in the subspace acts by symmetries. Okay, so here everything together. So your loss function will contain three parts. One data consistency part where you just try to fit the discrete Lagrangian to be compatible with the motions that you're observing. At the same time, some regularizer that I'll comment on in a second, and the symmetry parts. So the symmetry parts here measures whether LD is invariant under the V that we need to learn. So the V's are these elements in the Lie algebra, so think of just matrices that correspond to these variational derivatives, and at the same time you're trying to make sure that it's an orthonormal basis that you're learning, so you check normalization and orthogonality. Okay, so you're learning these two things at the same time. You first try to learn a one-dimensional symmetry group, then a two-dimensional symmetry group, and so on and so forth. So this will push the discrete Lagrangian to be symmetric. And this helps. So putting in these symmetry terms is better than not putting them in. So for instance, if you learn Kepler's problem, you learn a discrete Lagrangian without the symmetry terms, and then make a long-term prediction of motions, you get the green curve, which is qualitatively worse than the red curve, which covers the exact motion and captures this periodicity here in the Kepler problem. You can do exactly the same thing on the Hamiltonian side as well, right? So put the symmetry terms in while learning a Hamiltonian. So we've done this for the pendulum on a card. And you see what happens with the symmetry terms. So with the symmetry terms, so the prediction of motions covered exactly the exact motion in these long-term predictions. When you leave out the symmetry terms, you get the blue curve. So you get much worse behavior in long-term predictions. But the nice thing about this is that if you learn the symmetry terms, it is also system identification. So you identify automatically conserved quantities because symmetries correspond to conserved quantities by Noether's theorem. So if you've learned them, you can compute the conserved quantities that this corresponds to. So in this case, in the exact motions, the momentum is conserved in the horizontal direction, and the learned conservation law recovers this up to a small error, even though the noise is 10 to the minus 2, which is quite cool. And you also see that that the numerical motions here preserve the conserved quantity, while if you leave out the symmetry terms, it fails to do so. Okay, so regularization by symmetry helps for getting qualitatively better results, especially in long-term simulations, and it's also nice for system identification. But we need even more regularization because we want to be able to solve the discrete Euler-Lagrange equations, right? So now I'm gonna show you how to do this, and in the example case of PDEs. So now we are trying to learn a discrete Lagrangian density. So you can essentially come with any discrete Lagrangian density, but let's take this very simple one which just has 3 inputs. So you're trying to learn the discrete Lagrangian density to learn a model of an unknown PDE. So once you've learned this, you would need to solve these discrete Euler-Lagrange equations for computing motions or computing solutions to your PDE. So you look at those and think about, okay, what happens if I solve them with Newton iterations? Well, Newton iterations have a convergence theorem, right? So you know it will converge quadratically locally around a good gas. And then you look at these constants here. And one of the constants here is the smallest eigenvalue of this mixed derivative of the discrete Lagrangian density. The idea is now that if I get this term here to be small, the convergence will be very rapid and very quick. So I'm not just trying to learn the discrete Lagrangian now, but I'm also trying at the same time to make this term here, these constants, as small as possible. So I add a regularizer to my loss function that punishes small eigenvalues of this mixed derivative. And something simple like 1 divided by the smallest eigenvalue is already helpful. Sometimes you need a tamed version of it. But this is how you can push away these things from small eigenvalues and then get quick convergence. So you get a numerical analysis informed regularizer. And it's even guaranteed then to work, right? If you know you have minimized this regularizers, then you know at least close to training data, your equations will be solvable. And it works. So for instance, if you take wave equations, so you have some observations, you just have 80 samples of training data, they all look like this, and then you can learn the system and predict motions to even unseen initial conditions, and it extrapolates nicely, works. And there's a very nice thing. So we train this model on this kind of training data, which does not contain traveling waves. But then after learning, you can say, okay, let's look for traveling waves. And it will have the right traveling waves. And without having seen them. Right? And if you compare this, so what other people often do is that they say, okay, we have to learn a PDE, let's reduce it to the ODE case by just projecting all the training data to some learned latent space, and then learn an ODE on this latent space, and then later recover the full solution to the PDE. So, for instance, by principal component analysis in the spatial direction, right? And this, of course, works nicely. It works as well. So if I've got training data, I can do this, learn the discrete Lagrangian on the latent space, and then if I do simulations, I can recover anything that with initial conditions close to the training data. But of course, it doesn't work at all to find traveling waves there, because the latent space that I learned doesn't know that I want to look for traveling waves afterwards. So I will find something like this, for instance, which projection to the latent space solves the discrete Euler-Lagrange equations, which is completely wrong. Or if I start with initial conditions that should give me a traveling wave, and I project down, solve the system there, and then recover the solution, I also get nonsense, nothing that looks like a traveling wave. So we get a sheep model because we are kind of just training a very local stencil, right? And at the same time, we avoid these kind of problems that you have if you do model order reduction. And what you can also do is you can use, the mesh is kind of a design parameter. So you can also train your model on a very coarse mesh, and then look for traveling waves. And if you think about it, it's a coarse mesh, so maybe the traveling wave speed doesn't even match the mesh, and it works anyway. So you can do this with Schrödinger equation, a very low resolution mesh, and you find the correct traveling waves in the machine learned model. Okay, so to wrap up things, so I showed you how to learn models of dynamical systems from data and use regularizers that make sure that they perform well in the simulation phase by either trying to push it into a very symmetric representation, or in particular to use numerical analysis informed regularizers. So some regularizers that make sure that later on in the simulation phase that the discrete Euler-Lagrange equations that you need to solve are easy to solve and efficient to use in numerical simulations. Okay, so thank you.
Okay, thank you, Christian. I think there's time for one quick question. Okay, Okun.
Thank you for a really interesting and impressive talk. I wonder, when you add additional regularizing terms, how do you weigh the different terms? Is it a lot of, like, for every extra term you have to do more complicated hyperparameter search, or do you have some nice approach to weigh?
Well, not an automatic approach, right? So the idea is that, especially in the symmetry framework, I said it's a good idea to first look for a one-dimensional symmetry group and then add 2 dimensions and 3 dimensions. So a good idea is to switch them on as you're learning. So you would first learn without symmetry terms and then start switching on one by one, 1 dimension, 2 dimensions, until it stops working, right? And then you know, okay, I'm trying to look for a bigger symmetry group than there actually is. So that's the idea. But for these kind of regularizers that are numerical analysis informed, like this here, you need to switch them on at the very beginning, because otherwise your model would try to learn some discrete Lagrangian that is constant, which makes the data consistency term 0, but it has nothing to do with it. With the motions. So you switch them on at the very beginning and switch on the symmetry terms as you go along.